Hi, everyone. My name is Artemis Spyrou, and I'm one of the lecturers for the Nuclei in the Cosmos Summer School for 2021. It's unfortunate that we cannot all be together, but I hope that through this recording, you will learn something about experimental nuclear astrophysics, and we'll also discuss live during the school. Let me share my screen so we can get started. There we go. So my topic for these lectures is nuclear astrophysics experiments. Since there are more than one lectures covering this topic, we have coordinated, and I will be focusing more on the heavy element nucleosynthesis. Let me first introduce myself so you know who I am. So I'm originally from Cyprus. This is where I was born and I grew up. And this is for those who are not familiar with it. This is a map of Europe, and Cyprus is a little island country down here. So after that, I moved to Greece when I was 17 to start my undergraduate studies in the physics department in Thessaloniki, the University of Thessaloniki. So that's right here in the northern part of Greece. I stayed there for 4 years. And then I moved to Athens over here, again in Greece, where I did my PhD at an accelerator facility in the institute called Democritus and the National Technical University of Athens. So once I was done with all my studies in 2007, I moved to the US and I went to Michigan State University, which is over here. That's where Michigan is, or the Midwest. Michigan is highlighted here, and the Spartan helmet, which is the symbol of Michigan State University, that's where Michigan State University is. So I originally went there just for a couple of years to do my postdoc, but I ended up staying there, and I've been there now for over 14 years. So I went kind of through the ranks of assistant professor, associate professor, and now I'm a full professor in the Department of Physics and Astronomy. Outside of the lab and of the university and of work, I like various things and they change over time. So for a while I was a swimmer and I continue to love swimming. I was snowboarding for a while. Here in Michigan, there's a lot of snow, but not too many mountains, so it's a little more rare, but I still love to do that. I love to run. I'm very slow, but I still like it. I like to bake, especially with my girls. And here are my two girls. I have Mickey, who is 12, and Katerina, who is 8. And we also have a little puppy, not so little anymore. He's 4, and he's called Fivo. So that's who I am, and I'm looking forward to meet all of you when we meet for the school on Zoom, unfortunately. Okay, so the plan for the lectures I'm recording now, I'll record 3 lectures, so it kind of breaks a little bit and I cover all the topics, but in 3 videos. So in the first one, I'll kind of do an overview of heavy element nucleosynthesis, even though I know that you're getting other lectures that talk specifically about the various processes. I'll start with that so that we're all on the same page, and also then zoom into what are the nuclear physics inputs for each of these processes. In this first lecture, I will also cover accelerator facilities that we need to cover these experimental needs for heavy element nucleosynthesis. In the second lecture, I'll dive more into how do we do these measurements, of various different measurements. I cannot cover everything, but I'll cover as much as I can, focusing more on the things that I'm more familiar with personally, but we can discuss more if you have other questions. And then the third lecture, I'll cover more the nuclear structure aspect, which is a very, very important, also a very important aspect of experimental nuclear astrophysics, since all of these properties, the nuclear properties, play a big role in the various nuclear processes. Okay, so let's get started. Our observable, or one of our observables, it's not the only one, but one of our observables in the field of nuclear astrophysics is the abundances of the various elements. There are other observables like I don't know, the light from various stars in different wavelengths. I'm sure you will hear a lot about that, gravitational waves, and you'll hear a lot about all of these aspects in other talks. So I'm not going to focus on that, but I wanted to at least start somewhere, and I'm starting with the abundances. So we know that our abundances have specific patterns. They go up and down, and the reason for all these ups and downs is typically coming from the nuclear physics properties, and that's why it's a good starting point. So we know there's a lot of hydrogen, helium in the universe. There's a dip here in the first few elements, kind of goes back up. There's a peak right around iron. And then everything just drops to, this is a logarithmic scale, so it drops significantly. And then past iron, this is what we call heavy element nucleosynthesis. It's the elements that are above iron. And these are the elements that I'll be focusing mostly in this lecture. As I said, the reasons for these ups and downs, both around iron, lower masses, and also up here, you see kind of ups and downs in the abundances. These are all connected to nuclear physics observables, or nuclear physics properties and nuclear physics structure. So these are important to kind of understand what's going on. Okay, so we have the various abundances, and this is what we're focusing on. And one of the initial goals of the field of nuclear astrophysics was to understand where all these elements are coming from. So which astrophysical environment could make them, and what kind of nuclear physics process, could make them. So in the early days of the field, in let's say in the 1950s, the first few papers that came out that provided a comprehensive picture of this nucleosynthesis. That was the time that the famous B2FH paper, Barbich, Fowler, and Hoyle paper came out. I did not put a reference here, but I can bring it to the discussion. So they put together a comprehensive picture of how all these elements could be made. So the lighter elements, all the way up to iron, would be made mainly in stellar fusion. And this is where I will not concentrate on this talk. But then when you reach the region of iron, this is where things are getting weird. So up until this point, most of the reactions happening are charged particle reactions. But as you go heavier and heavier in mass, these charged particles, it's just getting harder and harder to fuse charged particles together, just because the Coulomb barrier is becoming higher and higher. Also, if you look at the distribution, the binding energy, the nuclear binding energy, there's a peak right around the region of iron, and then it goes down on both sides, which means that for higher masses, when we have this kind of fusion reactions, charged particle fusion reactions, there's energy released during these reactions. So this is very important, because this is what helps the star stay balanced, and this is what fights the gravitational collapse of the star. But if you go above iron, again, because of the Coulomb barrier getting larger, so there's no energy released from these reactions. So it doesn't only not balance the star, but it actually absorbs energy, so it would make that collapse faster. And so in the whole evolution of the star, things start to change right around iron. So as it becomes harder to have these charged particle reactions, nature figured out a different way of making the heavier elements, and that is mostly through neutron reactions. So there's a main process that is called the S process, which corresponds to a slow neutron capture. And for these, you would, the nucleus at each step, it will capture a neutron, go here in this chart, go to the right. And then because if this is a stable isotope, it could just wait there and capture one more neutron. But if this is an unstable isotope, it would have enough time to decay before the next neutron capture happens. This is why this is a slow process. So the neutrons are there, but they're coming slowly. And so this kind of process builds the elements heavier and heavier and just stays very close to the value of stability. An alternative to this, it would be called the R process. This is R for rapid. and it proceeds further away from the valley of stability. So this is a rapid neutron capture process. It has a very large number of neutrons available. And so with that, when a nucleus will capture a neutron and move here to the right, typically the half-life of that nucleus is long enough that there is another neutron capture happening, and then another, and just building towards more and more neutron-rich isotope. And that continues until either the half-life is too short and then you can have a beta decay, or the whole event is over and then kind of you're done. So through this R process, it proceeds through, again, neutron captures and beta decays, following a path that is quite further away from stability. And what we see here is that right around the magic numbers, the nuclear magic numbers, which are marked here with these horizontal and vertical lines, the path of the R process will kind of follow the magic neutron number, and it just stays there a little bit longer. What this does is it accumulates mass, it accumulates matter right around this region. And when the whole event is done and everything decays back to stability, there are peaks formed in our abundance distribution corresponding exactly to this location, just kind of project down, and then you will have a peak right around here. And if we look at the abundance distribution, then our process here is blue, and you see peaks. There's a peak here and another peak here, and these are formed exactly because of the magic numbers. There are corresponding peaks that come from the S process, and those are a little bit higher in mass because the S process will also find the magic numbers, but it finds them a little bit higher. And so the S process magic number would pop up here versus the R process would pop up a little bit lower in mass. So you can see the connection between nuclear physics and astrophysics already. We see this observable from the universe, the abundance pattern. And the reason that this has this shape is because of all of these nuclear physics basic properties, just the property of nuclei to have enhanced stability around these specific magic numbers. Okay, so another process that was originally introduced again in the 50s is what is called the P process. Now we also call it the gamma process. And today, at the time, they introduced it as a potentially proton capture reaction process, but we know now that it's mostly going to be gamma-induced reactions. So it's this weird process that starts at the top and kind of goes down. So it assumes that the S process nuclei, maybe even the R process nuclei were already formed. And then this is a process that pushes everything to the left here and just breaks them, emits, excites the nucleus through gamma rays. And then there's neutrons and protons emitted through photo disintegration reactions. And this was the complete picture. In the early days, this was the complete picture. We would have an S process, an R process, and a P process. Now it's 2021, and we know that things are a little bit different. Things are a lot more complicated compared to what it was introduced in the 50s. And we've seen now observables as our telescopes and our, just all of our tools become more sensitive. We start to see things that we could not see at that time. And so the more we see, the more we realize that this simple picture is not valid anymore. There are so many observables from stars that we cannot explain with just these three processes. We need to introduce new things to explain them. There are astrophysical environments that we're not even, we didn't even realize at the time. So there's a lot going on. The one thing I didn't mention here is the site for these processes. A lot is still under debate. We know, for example, that the S process is mainly happening in AGB stars. So that's kind of well known. The S process is the most well-studied process of all because it's right around stability. So our nuclear physics tools are well developed and available to attack this stable nuclei. The other processes are a lot less known. The R process, it was under debate for a long time if it's happening in neutron star mergers or if it's happening in supernovae, or it was just a big question. Now we know since 2017 with the observation of gravitational waves and electromagnetic signals from a neutron star merger. We know it is happening in neutron star mergers, but it doesn't mean that it's the only place that it's happening. So it's still an open question exactly how that works. And then the P process, we know it's in some kind of a supernova, but we don't know if it's just one type, like the core collapse supernova, or it can be type 1a supernova, or there are contributions from both. Okay, so going back to the new processes that were kind of introduced later on, and I'll mention briefly just 3 of them, just to, there are more, but I'll just briefly mention 3. One is the new P process. This was introduced in 2006. And it's definitely happening in the core collapse supernova, and it's the neutrino P process. So it's a process where it's kind of proton capture reactions mainly, but the fact that there are neutrinos around, they change the composition, they can convert some protons into neutrons, and so it's it just changes what's going on in the star and just creates this new process that could maybe contribute to the abundances we see. Another one is the I process, which is here in this purple color. I corresponds to intermediate. It's intermediate between S and R. It's intermediate in terms of the location on the chart of nuclei. It's intermediate in terms of the neutron density. And so the I process is maybe the most recently it has attracted a lot of attention because there are a lot of new observables that we've seen from stars that cannot be explained with just S or R or a combination of the two. We need something else, and the I process came to the rescue. And then finally, there's the RP process going here along the proton drip line. This happens during X-ray bursts. This is when a neutron star is accumulating matter from a companion star. And then once a lot of matter accumulates, then you have this burst of X-rays. Now, the fact that this is a neutron star, it's a very strong gravitational pull. And so whatever material is built there, whatever elements are built there, they're not really escaping out into the interstellar medium. They do not enrich the universe in new elements, but it's still an important process to understand because it's it is the most frequent explosion we see. And so we're trying to understand how that works. Okay, so this just kind of summarizes all the processes I'll be talking about. As I said, there's a lot more, but I will focus on this. We have to kind of zoom in. So let's say this is an experimental talk, so I wanted to start with where we fit into the big picture, at least the way I have it in my head. So one thing is that we have to have an observable. And this is what we see in the universe. It could be the abundances that I showed already, could be the light that I mentioned from X-ray bursts, could be gravitational waves. We have meteoritic samples from other sources in the solar system, spectroscopic information, gamma ray observations. There's a lot of observables. And so what we're trying to do is understand where all these observables are coming from. And so we create models. Here's the models that are trying to reproduce these observables. And our models started early on being very simple, and they're getting much more and more sophisticated these days. We have built even 3D models of supernovae, so they are getting more complex. But still, there's a lot of work still to be done from that point of view, but also we need to put in accurate input into these models if we hope to reproduce these observables in any realistic way. And so the input could be coming from the astrophysics side, which would be, just the conditions in the star, the density, the temperature, everything that's going on in the star. But then also the nuclear physics input, which is what we're talking about today. Nuclear physics could be experimental. If it's available, it's preferred, of course, to have the experimental answer. But a lot of this input we cannot get fully experimentally, so we always will need nuclear theory. And so a lot of the work we do experimentally is just to constrain nuclear theory in order to improve its predictive power, to say, okay, we can do well in this region where we have experimental data, let's extrapolate, and then we believe that this is going to do a good job. So we need both, but I will focus on the experimental side. Okay, so in terms of nuclear input, there's a lot of properties that we need, and I'll first briefly mention kind of the overview and then go into the individual processes and tell you what's needed in each of them. So we always need to know the masses of nuclei. Those masses come into play in everything from the nuclear reactions we are looking at, the decay properties, the binding energy I mentioned before. Everything depends on the nuclear mass. So this is probably one of the most basic property, nuclear property that we need in our calculations and in our experiments. And so the half-life, of course, plays a role, and we try to measure them as well as we can, or rely on theory to predict the ones that we cannot measure. I mentioned the binding energy already, and I mentioned where we have a peak right around iron. So yeah, binding energy is important. And then we dive into more details because details do matter in everything we do. So it could be the level structure. So you could do experiments where you're trying to understand, you do spectroscopy, you're trying to understand this level structure, the spins of the various levels, trying to extract properties, resonance properties and things like that. The angular momentum goes together with that. And then the shape of the nucleus also comes into play, maybe not completely directly, but indirectly knowing how the nuclear structure evolves along, let's say, a certain element. If you have data only up to a certain point, then constraining the nuclear shape or the nuclear structure, it could constrain your models to try and go a little bit further. In terms of reactions, of course, there's a lot of things needed from the nuclear reaction point of view. And some of this is done through direct measurements, like this is neutron or proton capture reactions, where you would have a neutron or a proton captured on the nucleus and just gamma rays coming out. So this is probably the most important reaction happening in the stellar environments. We have the beta decay half-lives and beta delay neutron emission. This is not quite a reaction, but I wanted to put it there just to, again, show its importance, because it's not just the half-lives that matter, it's also where is the neutron separation energy and how much of this decay is going to happen through the emission of a neutron or not. And so this kind of competition matters, and the competition between these two matter. Fission comes into play, especially in the R process, because we're pushing very neutron rich and very heavy in mass. And so these fission properties are very important. And then I wanted to mention here a couple of examples of reactions that are used indirectly to constrain some of the reactions we want to study. So transfer reactions would be the case where you would have, you just kind of sneak in a neutron or sneak in a proton into your nucleus to study this proton capture, this neutron capture reaction, even though you're not directly measuring the capture itself. So in this example here, there's a deuteron target and a proton recoil. So a neutron, we're sneaking in a neutron into the nucleus to study the neutron capture. Charge exchange reactions, this is the case where a proton is exchanged with a neutron or the other way around. And these could be used as indirect ways to study the beta decay, for example. So there's a lot going on there. I'm just kind of throwing things, keywords out there to get started with something, and just we'll see all of these as we go along. Okay, so back to our processes, and this is the same picture I showed before. And before starting to talk about how or what properties are important and how we're going to measure all of these properties, I wanted to focus what is it that it's important on each of these processes. So I'll start with the S process, which is right along stability. And this is the process that we know the most about. Almost everything is known. There's a few neutron captures that are missing because they involve long-lived radioisotopes. And so there's still work done in the community trying to measure or to constrain those missing neutron captures. If we go to the R process, this is probably the process that the least is known. It's quite far from stability. Most of our available facilities, accelerator facilities, do not give us access to the isotopes that are directly important for the R process. And so almost everything needs to be calculated by theory. There's some places where we can reach, like here, we can kind of barely reach the path, but the majority is out there. So this is a field that is quite open, and there's a lot of work being done to understand the R process. The quantities that we're mostly looking for are, of course, the masses, as I mentioned already, half-lives and PN values. This is the better delayed neutron emission. And then, of course, neutron capture reactions. Moving on to the I process, this is in between the S and the R, and in terms of what is known and what is needed is also in between. So almost everything for the I process is known. The masses are measured experimentally, the half-lives are measured experimentally. So almost everything is known. The one thing that is missing is neutron captures. There's almost nothing known in neutron captures on unstable nuclei, especially short-lived unstable nuclei. So this is, again, one of the open questions in the field, trying to constrain these reactions and inform our models. Going on the proton-rich side, for the P process, this goes into the proton-rich side, and there's a lot of these reactions that the majority of these reactions are not known experimentally. There's a few that are known right along the valley of stability, but if you go even a step away, there's almost nothing known in terms of P gamma reactions or alpha gamma reactions. I should mention that the reactions that are happening in the P process are gamma-induced reactions, so you could go to a gamma ray facility to measure these reactions directly. The problem is that if this involves radioactive nuclei, then this is not a measurement that we can do at a gamma facility. If your nucleus leaves for 2 seconds, then it's really a little bit unfeasible to have a target that lives for this short amount of time. So typically for this process, we've started to measure the reverse reaction, time reverse. And so this would be the P gamma instead of the gamma P, or the alpha gamma instead of the gamma alpha. And this, again, gives us enough information to constrain our models and put it into the P process. For the RP process, this is right along the proton drip line, and it's mainly proton capture reactions that are important. But for this one, it's also the masses and the half-lives. They're mostly known, but not all of them. And so this is, again, an active field of research. And then, oh, there it is. And then the new P process is also close to the proton drip line, not quite as far as the RP process. Again, masses and half-lives are mostly known, but there are very important PN reactions that happen here that this is probably the most significant input for this process. Okay, so you have the big picture. You've seen now what is needed. And so again, this is an experimental talk, and I will dive into how do we go about and measure all of these quantities and what is already known and what is still unknown. So I will start with just nuclear reactions in stars. I'm sure a lot of what I'm going to talk about, you will see in other lectures as well. We cannot coordinate every single slide. And it's also good to kind of, again, get everyone on the same page and we're speaking the same language within a certain lecture. The main focus will be on capture reactions, although we'll come back to other types of reactions later when we talk about indirect techniques. Okay, so let's start the simple picture. Let's say we have a stellar environment with two nuclear species, the X and the Y species. X is still, and the Y species is moving with some velocity v with respect to X. So we can figure out the rate of interaction between those two species if we know the number of X nuclei, the number of Y nuclei, this velocity over here, and also the cross-section as a function of that velocity. So this would be kind of in this simple picture that the two nuclei, the two species are separated in space and only one of them is moving with a fixed velocity, just a single value of the velocity with respect to the other. Of course, we know that this is not quite how things work. Probably our nuclei are all mixed together and there's a distribution of velocities. So we want to put that into our equation. And this would look like this. Again, the number of nuclei from each species matters. And then we have to integrate over the whole velocity distribution and the cross-section that corresponds to each of these velocities. So this would be what we call the reaction rate. We can measure this in the lab under certain assumptions and so on, and we can kind of translate that to how it looks like in the stellar environment, and this is what goes as an input into our astrophysical models. It's also useful to use a different quantity instead of the general reaction rate, to use the reaction rate per particle pair, and then it kind of comes out, the number of particles kind of comes out of the equation. And so we use this. If you've seen this symbol before, the sigma times u, this is what it means. Okay, another important part of this is that velocity distribution that we talked about. So this would look like this. And this is given by the Maxwell-Boltzmann distribution, and it comes as a function of the temperature of the stellar environment. So this is kind of a well-known quantity. If you have certain species in a particular environment with a particular temperature, this is what the velocity distribution looks like. Most of the time when we work with these quantities, we don't work with velocities, we work with energies. And so this is how you would translate the Maxwell-Boltzmann distribution of velocities into a Maxwell-Boltzmann distribution of energies. And if I plot it, it looks like this. It peaks nicely at low energies, and then it kind of tails off at higher energies. So we can combine these equations with the one we had before that gave the reaction rate. And so now our reaction rate as a function of energy and as a function of temperature looks something like this. It's not the most complicated equation in the world, and it's nice to look at and to use in terms of figuring out the reaction rate that we need. And so as an experimentalist looking at this equation, what I need is this quantity right here. What is the cross-section of a particular reaction for between two species as a function of energy? And so experimentally, I'll go in the lab and try to measure this quantity cross-section as a function of energy. Now, there's one more very important part to this, and it's not, we need to know the cross-section as a function of energy, but we don't need to know it everywhere from 0.0001 keV all the way to 10 GeV. There is a particular energy region that we need to know this, and this is the region that corresponds to the stellar environment, which has a couple of things folded in. So this is what we're talking about. So to figure out that important energy region, we need the Maxwell-Boltzmann distribution. You saw that already. And we also need to take into account the tunneling effect. This is the probability for a nucleus, for a projectile or a nucleus to penetrate the Coulomb barrier of another nucleus and still have a reaction happening, even though the energy is not above the Coulomb barrier. Classically, we would never expect a projectile to go through the barrier if it didn't have an energy that was above it. That's the classical approach, but through quantum mechanics, we know that there is a non-zero probability for that projectile to make it through, even if its energy is less than the barrier. So this is what's called the tunneling probability. It is increasing with energy. So this probability will get higher and higher as we get closer to the Coulomb barrier. And so this is a factor we need to take into account. So when we talk about the cross-section, then there are two parts. There is the one part, which is the interaction between the particles. So that's the pure nuclear. We just forget how this projectile made it through. It's out here and it's going to interact with the nucleus. What's happening then? What's that probability? And then the other part is the Coulomb force part, which is describing this probability. How is that projectile going to make it through? And so we can write our cross-section that we had in the previous equation using two different factors. One factor is what is called the astrophysical S factor, and it corresponds to pure nuclear properties. We just forget about anything Coulomb, it's just pure nuclear. And then this part over here is the factor that corresponds to the Coulomb barrier. This is important to have this distinction and to use the S factor mainly for practical reasons. If I look at my cross-section on a logarithmic scale, then that cross-section drops like a rock going to lower energies. And that's because of that tunneling probability that I mentioned before. The probability to penetrate that barrier and make it through and reach the nucleus is just getting so much smaller as we go to lower energies that the whole thing is just, the extrapolation is just crazy. So you have a very steep slope in terms of the change of the cross section as a function of energy, that if you only have measurements up here and the astrophysical region is this pink region here and you need to extrapolate, then it's not really clear how you're going to extrapolate. You can have big errors because of that. But if we take that Coulomb out of the equation and then the S factor, this is our S factor, on a linear scale, it becomes almost a flat distribution. And so that makes it a lot easier to extrapolate to lower energies. This is kind of the picture here, the dangers of extrapolation. If you don't really know what's going on or you're trying to make a guess, you could actually make the very wrong guess. So this is why it's important. We are paying attention to a lot of these things because experimentally we have access mostly to these higher energies up here, and astrophysically the important region is going to be down here. So we need to have convincing ways and smart ways to extrapolate down to low energies and get the right answer. Okay, so putting it all together, this is again the Maxwell-Boltzmann distribution. And the tunneling probability that we talked about would look like this. It gets smaller and smaller, as I mentioned already, as you go lower in energy. So those two distributions are both there in the star, and they're both affecting what is going to be the important region, the important energies that we need to measure at. And so if you fold those two together, then you get what is called the Gamow peak. This is our Gamow peak. Which has the gamma of energies, this centroid of the peak, and it also has a width. So this is the distribution. So experimentally, when we're trying to figure out what is the energy that I need to go and measure the cross-section at, then you have to know the temperature of the environment and what kind of nuclei are participating in this reaction that you're interested in. And then then there are relatively simple equations that you can use to get the centroid of the Gamow peak and to get, the width, and then you figure out where those measurements are going to be important. Here are some of the kind of the standard approximation for the Gamow window. There are other versions of this that give you slightly different results, but this is a good approximation kind of to start with. This is only true for charged particles. So we have to have like proton capture and alpha capture reaction, and this is what you would use. And so the window that we're talking about would be the centroid here, plus minus the width, this width divided by 2. So to get an idea of some of these environments and the different temperatures, the P process is taking place in temperatures between 1.8 and 3.3 gigakelvin. So some examples of P gamma and alpha gamma reaction Gamow windows would be, the P gammas would be between 1 and 5 MeV, and the alpha gammas would be between 4 and 12 MeV if you want to do the measurements. The RP process is a little bit lower in temperature, so we're talking about a little bit lower energies. And the new P process is kind of somewhere in between. And so again, these are the energies that are important. When we go to neutrons, there's no Coulomb barrier to worry about, but there is angular momentum barriers that we have to worry about. And so the equivalent of the Gamow window is going to be an angular momentum driven barrier. And so there's the angular momentum over here. So again, you have region and energy region that we're interested in. And so for the S process, this would be just a few tenths of keV, similar for the I process, and a little bit higher, maybe some hundreds of keV for the R process. So in terms of neutron energies, these are pretty low. Okay, so now we know what properties we need, what reactions, let's say, we need, and we know what energy we need to measure them at. Let's dive into how do we measure these nuclear reactions and the astrophysical reaction rates. So I want to start with this picture here, just kind of to distinguish between various the various different types of reactions that we could have. So for example, if I have a target nucleus, let's say A is my target nucleus, and I add a projectile. So this arrow here would correspond to projectile A in this picture. The mass difference between where this nucleus is and where the daughter or the final nucleus is, this mass difference is called the Q value of the reaction. And so for most of these reactions, the target nucleus is actually sitting a little bit higher, which means a positive Q value, which means that there's energy released after this reaction. Okay, so if it happens that the energy of my whole reaction in the center of mass matches exactly one of the levels in the final nucleus, we would call this the resonant reaction. So you have this reaction happen, you match exactly the energy. There are angular momentum considerations, but let's say everything works out well. And so you will hit one of these levels. That's what's called the resonance. If we go to higher energies, then all these levels that we see in the final nucleus start to get closer and closer and closer together. And they're so close together that we cannot distinguish between them anymore. So we cannot talk about individual properties. Then we have to talk about statistical properties, which just on average, this is what's going on in terms of the levels, their spins, and so on. So this is the statistical kind of reaction. And this happens at high energies. You populate the nucleus at higher energies. And this becomes more significant for heavier masses. So heavy element nucleosynthesis that we're talking about today, this is probably the most dominant reaction type. And then finally, you could have that low energy reaction that we're talking about, but it could be hitting right in between resonances. So it's still going to happen, but it's going to have a much lower probability than if it hits a resonance itself. So this is what's called the direct reaction, direct capture. So let's see a picture of what this could look like. And I imagine that one of the other lecturers, Professor Aldiota, is going to talk more about this. This picture I stole from one of her slides from a different school, but I like this picture and I wanted to share it. So all the peaks, this is a cross-section as a function of proton energy for the reaction magnesium 24P gamma. All the peaks that you see here correspond to those levels that I mentioned before. And so you see resonances. So you see these giant spikes in the cross-section. In between the resonances, you still have cross-section. It doesn't just go to zero. And this is the part that we call direct capture. And then as we go heavier and heavier, you cannot really see it here, but the resonances will start to get closer and closer together. And that's where the statistical regime starts. In magnesium 24 or aluminum 25, this is a very light nucleus, so this will happen at much higher energies. For heavier nuclei, this starts early on. It might be already at 1 MeV, 2 MeV might already be statistical. Okay, so all of these were for the incoming channel and kind of matching what's going on with the levels of the intermediate nucleus. Let's see what's happening in the outgoing channel. So our outgoing channel here would be, in a capture reaction, would be the same nucleus that we produced, and it was excited at some high excited state. It would just emit gamma rays and go down to the ground state of this nucleus. So this is why it's called a radiative capture. It just emits gamma rays after capturing a particle. So this would be the simplest case. You just have the reaction happen. There's a bunch of gamma rays coming out. We measure those gamma rays. We can figure out what the cross-section is. There are more complications, of course, because it could be that if the populated state is sitting above the neutron emission threshold, so in this case, the neutron emission threshold will be here, where the daughter -1 neutron is sitting. Then in this case, you could have gamma rays coming down, but you can also have neutrons. And actually, this would be the dominant channel. You can have neutrons emitted. And so this would not be, if there are neutrons emitted, then it's not a radiative capture anymore. And so the competition between these two, of course, matters in these environments. Then the other thing that could happen is that this final nucleus here is actually unstable. And if it is, it will beta decay. So it could beta decay and then populate various levels in the final nucleus C. And then again, we can measure the gamma rays. And we can use this when we do the various techniques. we will be able to use this technique, this beta decays and these delayed gamma rays to measure our cross-section. And then finally, it could be that this nucleus is populating high-lying states that could also emit neutrons. And so this would be the beta delayed neutron emission. So there's a lot going on. In the simplest case, when in a proton capture reaction or alpha capture reaction or neutron capture reaction, if you are lucky and you populate the nucleus at relatively low energies, then you don't have to worry about anything else. But this is not always the case. And so it's good to keep an eye on the various competing channels. It could also be that it's not a neutron that is emitted here. It could be that it's a proton or an alpha particle emitted. And so all of those computations matter. Okay, so let's say that we want to calculate the cross-section for a specific reaction. And this would be using what's called the Hauser-Feshbach theory, or this is the statistical model. So in the case that we have a capture reaction happening, you populate this intermediate nucleus, and then you have various channels coming out from that final nucleus, and we want to calculate the cross-section. So what we have here is basically the spins of the various nuclei that are involved. And then the important part is this last part here. It's a sum of over everything that's available in the reaction. So we have the incoming channel, we have the outgoing channel for the specific reaction we're interested in, and then we have a sum of all possible outgoing channels. And this is what we need. And this is why knowing the competing channels is very important. It's not just important to measure, let's say, the gamma rays coming out, but it's the competition between that gamma ray channel versus neutron versus proton emission that matters. And that's coming into this factor over here. So if you want to calculate a cross-section, then we need to know all of this. So these T's that you see here are called transmission coefficients. And so this is the part that it kind of combines both the incoming channel properties. So, so this is this part, and the outgoing channel. This is this part. In terms of the incoming, well, depending on what particles or what gamma rays you will have, if it's particles, this is described by what's called the optical modal potential. So this describes how, let's say, a neutron will penetrate the nucleus to have a reaction, or it will be emitted, or the same for a proton and so on. And the gamma ray strength function is a similar thing for gamma rays. Now, it could also be that, so this would be true for individual levels. And so we can calculate the cross-section for individual levels. But if we're getting into the statistical regime where these individual levels we cannot distinguish anymore, then the transmission coefficient will look something like this, where we're summing over all of the known discrete levels. And then we're also integrating over all of those levels that we cannot distinguish anymore. And we integrate with folding in the nuclear level density. That's the rho over here. And so in terms of quantities that are needed, we would need the gamma ray strength function, the optical modal potential, and the nuclear level densities. This is important to keep in mind when we do indirect reactions. If you experimentally can go in and you can measure the reaction you're interested in, then typically none of this matters. You just measure your reaction, you have your result, and you can put it into the astrophysical calculation. But if you cannot measure that reaction directly, then all of this matters, because if you know nothing about a reaction, but you have a way to measure the optical modal potential, you're already constraining it. Or if you can measure the gamma ray strength function or the level densities. And so this is a very important aspect, both on calculating these properties or these reactions, and also providing indirect constraints for these reactions. So just to see the impact of some of these, I have an example here for a neutron capture cross-section. This is strontium-95 and gamma. This was done with a statistical model code TALIS. This is an open source code, and you can download it and do these reactions yourself. So this is an N-gamma reaction. These are, again, the three quantities that I talked about. If we use, so within TALIS, there's various models that predict all these different properties, and I just have, again, keywords here that you can use. But if I vary the level density using these various models, then I get a variation in my cross-section, which is, I don't know what that is, maybe a factor of 5 or so. If I do the same with the gamma ray strength function models that are available within TALIS, then I get maybe closer to a factor of 10. The neutron optical potential is actually not so uncertain in this, at least in this region. It becomes more uncertain as you go further away from stability. But here it's maybe a 10% effect. It's not more than that. And then we can put all of this together and see what is the uncertainty or the theoretical variation in predicting a neutron capture cross-section. And it's quite large. This is, I don't know, a factor of 50 or something. So this just tells you why on the experimental side, we need to go and measure or constrain these as much as we can, because right now we're just relying on theory. These theories are not well constrained, far from stability. And so the predictions just vary significantly. Another thing I wanted to mention is that I said the neutron or proton optical potential doesn't vary significantly. This is not the case when we have alpha reactions or the alpha potential. And this is just one example of the Moly 92 alpha gamma reaction, where just using different alpha potentials and nothing else, we get a factor of 10, at least a factor of 10 variation in this cross section. And so the alpha potential is another thing that is an open question. Okay, so we talked about a lot of things. We introduced the various processes, what's needed, and then kind of looked at the big picture of how do we look at the reactions that are happening in stars, and how do we look at that from the experimentalist's eyes. What's important, what do we measure, what do we need to measure, so on. So now we're going to jump in and see how we can measure all of these things. And there are many, many different ways. And again, I'm not going to cover everything, but I will cover a sample so you can get an idea. So the yield of a reaction, we call that Y, would be the number of reactions divided by the number of beam particles. The cross-section itself is coming from the yield of a reaction divided by the number of target particles. So in the end, it's three quantities that matter. It's how many reactions happened, how many beam particles were there, and how many target particles were there. This is the same as the astrophysical environment, right? It's we had the number of X nuclei, the number of Y nuclei, and the cross-section, the probability for those to interact between them. This is the same thing here. And so experimentally, you would need to know how many reactions happened, how many beam particles you had, and how many target particles you had. And this is experimentally, this is the bread and butter of the experimentalists. It's not easy to measure. All of these have to be absolute quantities. I need to know there was 10,000 reactions that happened. So it's not relevant, it's not related to something else or relative to something else. It's the absolute number. And so that's what makes these cross-section measurements hard. So to measure this cross-section, this is what we need. But first, before we even dive into that, we would need a beam to have these reactions happen. And so for this first lecture, I'm going to focus on the beam facilities. How do we get a beam? And we'll dive into these various measurements in the next lecture. Okay, so accelerator facilities. These have been around for quite a long time, and there are different types of accelerator facilities. The classic or traditional one is stable beam facilities. I teach the properties of, the principles of these accelerators in my introductory physics course for first-year students. So I am sure that all of you have heard about how these accelerators work. So I'm just going to give a broad overview. We could have a cyclotron where you have just different electric fields that make your particles go faster and faster in here. And you also have a big magnetic field that helps constrain those particles in space. And once the particles go as fast as you want them to go, then you extract the beam and you have your nice accelerator particles. There are, room temperature kinds of cyclotrons. There's also superconducting cyclotrons today, and there are state-of-the-art cyclotrons. These are very compact accelerators. So in most of medical facilities, this is the type of accelerator they choose to have. It's just easier to use. We could also have what is called a Van de Graaff accelerator. It could be single-ended or it could be a tandem. Single-ended means that you have the large voltage that comes out of a Van de Graaff. So it would look like this. I'm sure you've seen it in demos and stuff. You just have a large voltage coming out. And so your particles, your charged particles will feel that voltage, get accelerated, and then you can use them for your experiment. Or they can get a double kick. So the accelerator would be in the center. They get the first kick. Then there would be either a gas or a foil in the center to change the charge of those particles. And then they get a second kick if they have the opposite charge. And then finally, there's a generic category called Linux. This is just linear accelerator. This is probably the most modern accelerators look like this, because you can upgrade them to higher and higher energies by just adding new modules like these orange modules that you see here. You just add more and more, and then you have higher energies. And so this is the more flexible and more modern version of these accelerators. Some basic components here. This is the accelerator where I did my PhD a long time ago. This is in Athens, in Greece, at a lab called Democritus. It's a 5 megavolt tandem accelerator. So you would start with an ion source that produces those ions. Maybe it's protons, maybe it's alpha particles. Typically, these have relatively light elements that are produced. And then the accelerator itself is a Van de Graaff accelerator sitting right here in the center. So you would get the charged ions coming out of the sources. They get a first acceleration. And then here in the center, at least at the time when I was a student, it was just a foil, just a very thin carbon foil. As the ions go through, they change their charge. And now the new charge will feel a second kick and they get accelerated a second time. This is why it's called a tandem. Then what's coming out is not 100% pure. You have the different charge states of your ions. You could have, some of these carbon ions that are kicked out of the foil coming out as well. Whatever it is, you need a magnet to separate out what's coming down the pipe and just choose the one that you're interested in. And then you send it into the various experimental stations. So this is the general principle. There are different variations of this, but this is the general principle of these kinds of stable beam accelerators. The kind of state of the art of our field is radioactive beams, of course. So as we're trying to reach these processes like the R process, the P process, the RP process, we need to have these very short-lived radioisotopes. And the stable beams that we've had up to now are not enough. So we had to be creative. And this has been happening for several decades now to produce radioactive beams. There are different ways that you can produce those radioactive beams, and I'm trying to give you a big picture here. Again, I might have missed some of the labs that use it, but this kind of gives you a good idea of what's going on. The first principle is fragmentation. So you see there's a lot of labs around the world that choose to use this. The idea here is that you start with a fast, stable beam. Fast meaning at least 100 MeV per nucleon, can go all the way to a few GeV per nucleon. You get this fast beam and you hit it on a target. This fast beam typically is a heavy beam. Most labs can typically go all the way up to uranium. And so you get this heavy beam, you hit it on a target at these high energies, and what happens is that this beam just breaks into pieces. It's fragmentation. And so when this fragmentation happens, you have a whole lot of species, nuclear species coming out. It could be, 100 different nuclei, different types of isotopes coming out. So you have to have a very good filter, a very good separator to separate out the ones you don't want and keep the ones that you do want to use. So all of these facilities have very good separators that filter these beams, and you end up with a nice radioactive beam. Typically, these are not pure, 100% pure. Typically, there are a few species, maybe 5, 10 species coming down the pipe together. But at these high energies, you have the flexibility to have diagnostics. And so you add a thin detector in the path of your beam, and you see when the beam hit that and when did it arrive in your setup. So you have a lot of diagnostics to identify and separate these different species. This is not true when we're dealing with low energies, where you cannot really put anything in the path of your beam, otherwise it will stop and you will lose it. The isotope separation online, or ISOL technique, is also a quite popular technique. It's used at various different labs. And here, the idea is that you would get a stable beam, typically a proton beam. It hits a target again, and now the target is something heavy. And the reactions that are happening here, you are producing a bunch of these different isotopes, the rare isotopes. And then through chemical processes, you have to extract these isotopes from your target. And then again, you go through separation and reacceleration, because these are now very slow, and acceleration to get them into your experimental setup. This is a very powerful technique. It produces very strong beams of particles, but it can only work for specific elements. It cannot work for everything. There are chemical elements that will just not diffuse out of this target very easily. So no matter what you do, they will just never make it out of the target. So those are hard to deliver with these kind of facilities. Those can be delivered with the fragmentation facilities. Fragmentation facilities can produce everything independent of chemistry. The problem there is that it might be a little weaker than, so these facilities typically have stronger beams for the ones they can produce, but they cannot produce everything. Fragmentation can produce everything. So this is kind of the general idea. And so those kind of facilities are complementary to each other. A new idea was introduced a few years ago, which is the Caribou facility at Argonne National Lab. It's in outside of Chicago in the US, where what they did was grab a fission source. This was initially a spontaneous fission source of californium. And so out of all the fission fragments that are coming out, you see a distribution over here. If you have a good extraction and separation technique, then you can isolate the ones that you want to study and send them down to the experiment. And this is exactly what they did through extraction, separation, and acceleration. And so they provided beams of isotopes that were just not available anywhere else with these other facilities, or not as strong. So they provided a unique capability. Now this facility is upgrading next year to a neutron-induced fission source. And so this will add more capability in terms of the flexibility for different kinds of fission sources. And finally, you can have radioactive beams produced at the classic stable beam facilities. And those are typically through low energy reactions on lighter elements. And so you would have a low energy stable beam hitting a target. And then out of the reaction that's coming out, if you have a good separation, maybe, then you could produce a radioactive beam to use for experiments. And again, a lot of these facilities have produced these radioactive beams, mostly focusing on lighter elements. So let's give you again the big picture of what these radioactive beam facilities, what they could do. One example, not a very random example, this is a facility I've been doing experiments for the last 14 years. So it's very close to my heart. This is the National Superconducting Cyclotron Laboratory at Michigan State University. It just closed about a year ago. So we finished running experiments, and it gives its place to the new facility in the US, which is the facility for rare isotope beams. So this facility here used two cyclotrons that were coupled together to bring the energy up to about 150 MeV per nucleon. This is where the target would be that I talked about in the previous slide. This is where the fragmentation would happen. And then this orange part is our fragment separator, the filter that would separate out the things we didn't want from the things, the one beam that we were interested in. There are a lot of different experimental stations, depending on what kind of reaction you wanted to measure. This measures neutrons. This will go straight and gives decay properties. This S800 spectrograph was used with a variety of different complementary detectors for gamma ray detection, for charged particle detection. And we also slowed down these fast beams to do laser spectroscopy or mass measurements. And then we also built a re-accelerator to accelerate these beams to below Coulomb barrier energy. So low energy is perfect for astrophysical applications. So it's a large facility, and everything you see here stays. So starting from this point on, all of these stay, the experimental equipment. And this first part is replaced by the new facility, the facility for rare isotope beams, or FRIB, where instead of the two cyclotrons, I mentioned before that the state of the art is linear accelerators. And so we have a linear accelerator to produce much more intense beams than what we could do with the couple of cyclotrons. Okay, switching gears now, I'll talk very briefly about neutron facilities. So a lot of the measurements we need involve neutron beams. And so there are two main types of facilities out there. One is what is called the time of flight type. So you would have a neutron beam produced in a bunch mode coming from a proton beam. So you would have high energy protons hitting a heavy target. And then as I said, this is bunched, and so you know exactly when the neutron started, and then you see when the neutron arrived at your setup, and based on this time of flight, you can figure out the velocity of the neutron, and from that, its energy. So it is typically a continuous spectrum of energies. They're not monoenergetic neutrons, but you can figure out what energy they correspond to and kind of get, with one experiment, get the whole energy distribution. Another way to do these measurements through quasi-monoenergetic neutrons. And so this is a reaction-based, well, this is also reaction-based, but this is, you know, different types of reactions. And so depending on the energies of the neutrons that you need, you could use a DD reaction or a DT or a P lithium 7. So again, there are various reactions. And I have here maybe a question that you can think about, we can discuss later. Let's say you have a reaction like this, how could you get to as low energies as 25 kV that is needed for example, S process or I process measurements? Okay, and the final type of facility I'm going to talk about is gamma ray beam facilities. And these are, again, mainly two types of facilities, I would say. One is Bremsstrahlung based, so you have an electron beam, electron accelerator. So any facility really with an electron accelerator could do this, whereas the electrons slow down in some material, they emit this Bremsstrahlung radiation. This is a continuous spectrum. They're not monoenergetic gamma rays, so you need to kind of gear your experiment and correct for this broad distribution. Or you can do what's called the Compton scattering, which is more of a monoenergetic kind of beam. And again, there's some facilities. And I'm showing here as an example, this is a Higgs facility in North Carolina, where they do this kind of measurements with kind of monoenergetic gamma rays. I don't want to go into too much detail, and it's also not my expertise, but I wanted to mention it just so you have the big picture. So I'll stop here in terms of the first lecture and come back to how do we measure all these reactions in the next lecture. See you soon.